Okay, now that you have read through about the general idea about the two types of errors that we will see when using these polynomials to approximate functions, alternating series error, where the next term is the error, or a Lagrange error bound, where you will have to maximize the derivative in order to get the biggest error bound possible. So let's take a look at a couple examples. So the first example is, I want to, first question asks you, find the third degree Maclaurin polynomial for sine of x. So I went through, calculated the first three derivatives. This is my polynomial right here. And I want to figure out how accurate this polynomial is to the function sine of x, which is what I'm working with. So I know that the sine of x is exactly equal to the first terms of the polynomial plus, this is called my remainder. So whatever gets cut off is the error associated with this polynomial. And what we learned from the reading before is that your error bound, which is called your remainder, is going to come from the next term over. So since this is the third degree, the next term will have the fourth derivative. So I'm going to come up with the general term that has the fourth derivative in it. Okay? And let's plug in all the pieces that we know. Well, this x value I know is going to be 0.1. It's whatever value that you are actually figuring out. So I want the sine of 0.1, so this x is 0.1. This c value is where it is centered at. This is a Maclaurin, so I'm going to plug in 0 for c. I have 4 and over 4 factorial. This piece right here, we are trying to find the biggest error possible. So you need to maximize that value of the derivative to make this term the biggest value possible. This is very easy if you're talking about a sine or a cosine function, because the biggest value a sine or cosine could possibly take on is 1. So we're always going to just use 1 for sines and cosines. So whatever this value is going to be the biggest error bound. And if you type this in your calculator, we're going to need to use scientific notation. This is the error bound associated with just using a third degree polynomial to approximate sine of x. So notice if you actually write these numbers out, it's 0.0004167, so that's a pretty small error bound. So the actual value, if you use your calculator, of sine of 0.1 is 0.099833. The value of the polynomial at 0.1 is 0.099833. So the actual error, which is just the difference of these two numbers, is 8.33 times 10 to the negative 8. So what this number gives you here, this is called your error bound. So it is the biggest error possible. So this actual error should be something less than the error bound. Okay, let's try another example, and maybe an example that is not sine or cosine. Okay, there's a typo in this next problem. Let's try to find the error associated with natural log of x, centered at x equals 1. And we did this previously on page 39, example 4. And we already came up with the polynomial if we look back, so I won't go through that again. And this is the polynomial that we came up with. And I went through and reduced the factorials. So this is what we came up with. Okay, the actual value of natural log of 1.1 is 0.095310. So let's see how good this approximation is. So again, this is asking you to find the error associated with using this third degree polynomial. The error is going to be something less than or equal to the next term over. So the next term will contain the fourth derivative times x minus c to the fourth over factorial. And when we talk about errors, we only care about absolute value. Okay, so let's plug in the pieces. Okay, I'm going to start with this. The x value is whatever value of x that you're plugging in. I want to know what happens at 1.1. So I'm going to plug in 1.1 for x. My c is where you are centered at. The original problem said you are centered at 1. There's your minus 1. And then I have a 4 factorial here. This is the piece that's always the trickiest to find. For sines and cosines, you're always going to use 1 because those are bounded functions and the biggest value they can take on is 1. And we talk about the absolute value, so it doesn't matter if it's 1 or negative 1. For any other function, you will actually need to calculate that particular derivative. So if the original function is natural log of x, you will need to come up with the fourth derivative. So your first derivative is 1 over x, etc. And if you go all the way to the fourth derivative, you will get to here. So you need to maximize this derivative on the interval from where you are centered at and the value of x that you are trying to actually find. And it will always be one of these endpoints. It will not be a number in the middle. So the biggest value this will take on is when z, which is really your x, that's what that z stands for, is going to be when z, or this x here, is 1. So the biggest value of the fourth derivative at z is really going to be -6 if I plug in z and for x here. So I'm going to plug in -6 here. And again, it doesn't matter that it's -6, we want the biggest absolute value. If you punch this out on your calculator, you'll get 2.5 times 10 to the -5th. So this is your error bound. If you try to find the exact error, which is taking the actual value of the log and subtracting off from the polynomial approximation, the exact error is this. So notice this is something smaller than the error bound that we came up with.